Introductory Nuclear Physics course, and today's topic is quantum theory of atoms. I am Dr. Nasir Majid Mirza. I will be discussing today how quantum theory was developed for atoms and the electrons, and what fundamental changes it brought to the atomic model. If we recollect the ideas on limitations of Bohr's atom, we see, first of all, the Bohr's model was applicable only to hydrogen. One electron ions, such as helium plus, lithium plus, it does not even work for ordinary helium. Bohr's theory cannot explain why certain spectral lines are more intense as compared to the others, and why certain transitions between the energy levels have greater probability of occurrence than the other. It cannot account for the observations that many spectral lines actually consist of several separate lines whose wavelengths differ slightly. And perhaps most important thing is that it does not permit us to obtain why really a successful theory of atoms is not making it possible to understand how individual atoms interact with one another. So we cannot understand the aggregate macroscopic behavior of matter using Bohr's atom. So physical and chemical properties are really obscure to us under the Bohr atom. So the quantum mechanics birth took place, and it is really after the establishment of the analogy between light and matter that was made in 1934 by de Broglie. And his work on the footsteps of Einstein and Comte. De Broglie postulated that early ideas about the light waves having the particle nature, he postulated that each particle with a momentum p will have an associated wave and wave of wavelength lambda, which is equal to h divided by p, and h is the Planck's constant, p is the momentum. Experimentally, it was seen further that electrons diffract just like waves, just like light. De Broglie's waves were really associated with the microscopic particles like electrons. So quantum mechanics was then developed to account for this dual nature of matter. That is, matter is based on particle and wave duality. In quantum mechanics, we describe particles by wave packets or collection of waves. We say that it is representing a range of momenta delta p around p, or delta p at x position with the amplitude of delta x. The information about the particles is within the wave packet, and it is within the localized region of space. So quantum mechanics has a main quantity which is concerned with the microscopic particles, and it is described through a wave function psi. Psi itself has no physical interpretation. Square of its absolute magnitude, the psi absolute squared evaluated at x and t is proportional to probability of finding a particle or a body there at position x at certain time t. So linear momentum and angular momentum and the energy of the body all are the quantities that can be estimated with the help of this wave function psi. So problem with the quantum mechanics is how to determine the wave function psi for a given body where its freedom of motion is limited through the action of external forces. The external forces or the potentials in which this body is placed. Wave functions are usually complex functions, and they have both real and imaginary parts. So probability then must be a real positive quantity. So probability density of this complex wave function psi is therefore taken as the product of the wave function with its conjugate, with its complex conjugate. So psi multiplied by psi star, which is the complex conjugate, is the probability density. Density stands for the probability per unit volume. Since this psi squared is proportional to the probability density of particle to be found at certain position, then it is described by the wave function psi, then the integral value of the psi squared over all space must be finite because body is somewhere after all. So if we find the integral equal to 0, the integral from minus infinity to plus infinity for all the volume and for all the times, then it is not there. The particle is not there. But if particles do exist, then this integral obviously cannot be infinite and cannot be 0. So it must still mean something. This is called normalization condition. Normalization of the wave function squared, or the probability density multiplied by the elemental volume and integrated over all possible volume, must remain equal to 1. And such a condition is termed as normalization condition. Since particle exists somewhere at all the times, so probability of finding it will be equal to 1. The quantum mechanics has a fundamental equation called Schrodinger's wave equation. It is the fundamental equation of quantum mechanics. It is similar to the second law of motion, as the second law of motion is for the Newtonian mechanics. The variable is wave function psi. The time-dependent one-dimensional Schrodinger wave equation is given by the following formula, and let's describe it. It is iota times h cut multiplied by the partial derivative of psi with respect to time. H cut is h divided by 2 pi. H is Planck's constant. The partial derivative with respect to time of psi, the wave function, equal to minus times h cut square divided by 2m multiplied by the second derivative of psi with respect to x, the space variable, plus u times the psi. The u is the potential energy operator, and psi is the wave function. For the three-dimensional Schrodinger's wave equation, the time-dependent form is given by the following. It is again iota times h cut times the partial derivative of psi with respect to time equal to minus h cut square divided by 2m multiplied by the three terms that are added together. The first term is the second derivative of psi with respect to x. Second term is the second derivative of psi with respect to y. Third term is the second derivative of psi with respect to z. And all these summed together form the space derivatives or space operations on the wave function, plus the u times psi. The u times psi, the u is the potential energy operator. It is called particles potential energy, and it is function of x, y, z, and perhaps function of t as well. The result, I'm not going to solve this three-dimensional or one-dimensional Schrodinger wave equation for you. It will be covered in some other course. But the results are obviously very important, and I must describe those results. The results are primarily in the form of the quantum numbers. The first quantum number is the n. N is called principal quantum number, and it obeys the following. It is basically discretization of the energy, E sub n. The n means that it is significantly related to n, and it is dependent as 1 over n square. The rest of the term is a constant. And with the minus sign. So the E1 divided by n square, we can write it like the constant. If n is equal to 1, then the energy is E1, so it is the lowest or the ground state energy. And n is equal to 2 and n is equal to 3, the values start changing. However, they are discretized values. They are not continuous variation. N has a discrete value. The condition that n must obey is that it must remain equal to or greater than L plus 1, where L is called the orbital quantum number, and this is expressed in the following form. L can have values of 0, 1, 2, 3, and so on, up till n minus 1. The constant, another which comes from the Schrodinger's wave equation, is ML, and this is known as magnetic quantum number. It is magnetic quantum number for hydrogen atom, and it must obey the following rules according to the solution of the Schrodinger's wave equation for hydrogen atom. ML can have value 0, plus minus 1, plus minus 2, up till plus minus L. So it depends on L. L depends on N. N actually has the energy dependence. So let's briefly discuss the principal quantum number. Classically, we very well know that the total energy can have any value. The negative bounded systems show, the bounded systems show the negative value. And the positive energy is seen in the free systems. So in quantum theory of hydrogen atom, we come to know that the energy of the electron in atom remains constant. However, it will have positive values for ionized atoms and negative values for the bounded electrons. And the energy is expressed in this form, that En is equal to E1 divided by n square. E1 is the ground state energy, and these are the negative values. Negative values mean that they are for the bounded electron. N can have any value, 1, 2, 3, and so on. So the quantization of electron energy is occurring here in hydrogen atom, and it is described through quantum number, which is principal quantum number, and the electron can have only discrete energy values, and the lowest value in the minus sense is E1. The other quantity is the angular quantum number, and it is basically based on L. The electron quantum angular momentum for the hydrogen atom is described by this magnitude L, which is under root L into small l plus 1 times h cut. So the orbital quantum number L is basically restricted through this condition that L can have value 0, 1, 2, 3, up till n minus 1. So the angular momentum can have only fixed values, and their fixed values of the angular momentum are both conserved and quantized. and the h cut, which is h divided by 2 pi, and its value is 1.05 1.054 into 10 to the power minus 34 joules into second. It is a natural unit of the electron angular momentum. So any angular momentum of electron will be seen as some form of h cut. And the small l will be dictation, which will come to tell us that they are having discrete values. The angular quantum number and the electron's angular momentum states are designated through the spectroscopic notation as well. For L is equal to 0, the notation is S, the S state. L is equal to 1 is P state. L is equal to 2 is D state. L is equal to 3 is F state. L is equal to 4 is G state, and so on. So a state in which n is equal to 2 and L is equal to 0 is basically 2S state. If n is equal to 4 and L is equal to 2, then 4D is the state. So this kind of a table is available. Here n is equal to 1 can have 1S. For n is equal to 2, 2S and 2P are possible. S means L is equal to 0. P means L is equal to 1. L is equal to 0 states are all S. L is equal to 1 states are all P states. L is equal to 2 states are all D states. We see also that for n is equal to 3, we cannot have L is equal to 3. It will remain less than 3. So S, P, and D are possible. That is, L is equal to 0, L is equal to 1, L is equal to 2 are possible for 3, n is equal to 3, and so on. So we can see how the table is filled. The magnetic quantum number and its significance. We must make further clarity that the orbital quantum number small l determines the magnitude L. That is, the angular momentum's magnitude is determined. So we come to know that the electron's angular momentum is basically a vector quantity, just like linear momentum. And to describe it further, we need to specify the direction. So we know the magnitude, but we don't have a clue about the direction. So when the fingers of this right hand are pointing towards in the direction of the motion, then the thumb is showing the direction of L. This rule, the thumb's rule, is shown here in the figure. So now the magnitude of the quantity called the magnetic quantum number, ML, is specified for the direction of L. So it determines the component of L in the direction of the field. The phenomena is often referred as space quantization. So if we let magnetic field direction parallel to Z direction, the component of L in that direction is given by Lz, which is equal to the ML, the magnetic quantum number, multiplied by h cut. ML can have values of 0, plus minus 1, plus minus 2, up till plus minus L in terms of h cut. So the space is also quantized. Not all the directions are allowed for the angular momentum to have. Some specified directions are only allowed in the space. So possible values of ML for a given L range from plus 1, plus L through minus L. So number of possible orientations of the angular momentum in the magnetic field are 2L plus 1. Now, let's see if L is equal to 0, then the Lz can have only single value of 0. If L is equal to 1, then Lz may have h cut 0 and minus h cut values. If L is equal to 2, then Lz can have possible values of 2 h cut 0, minus h cut, minus 2 h cut, and so on. So if I go through summing the overall picture of the electron in hydrogen atom and its quantum states, then 3 quantum numbers are allowed, and their possible allowed values are given by these things. The first is the principal quantum number, second is the angular quantum number, third is the magnetic quantum number, the N, L, ML. The first is related to energy, second is related to the magnitude of the angular momentum, third is related to the direction of the angular momentum vector. The values it can have are that N can have 1, 2, 3, and so on. L can have 0, 1, 2, 3 up till N minus 1 value. Magnetic quantum number can have 0, plus minus 1, plus minus 2 up till plus minus L. So if I do look into the ground state, for N is equal to 1, only choice is L is equal to 0. Therefore, ML is fixed 0. So the complete ground state is given by 1, 0, 0. The N, L, and ML values in a complete state, and we can say that this is the address of the ground state electron. The first excited state is N is equal to 2, and for that L is equal to 0 or L is equal to 1 possibility. L cannot be 2. For L is equal to 0, ML is 0, and for L is equal to 1, ML can be 0 and ML can be plus minus 1. And therefore, we have these choices. And we can see these choices are with us that are 2, 0, 0, 2, 1, 0, 2, 1, plus minus 1. So there are possible 4 states for L is equal to 1 and 1 state. So total 5 states are possible for the N is equal to 2, the first excited state. Knowing the quantum states of the electron, knowing the principal quantum number, the angular quantum number, and the magnetic quantum number, we have arrived at this conclusion that the energy of the electron is discretized. It can have fixed energy states. The lowest energy is the ground state. Infinite energy, infinite N is equal to infinity stands for the energy equal to 0. And then positive states mean that the electron is free. The angular quantum number indicates that all electrons in bounded hydrogen atom have the discretized angular momentums. The possible angular momentums are fixed. And their direction in space is also fixed, and it is the space quantization which is occurring with the help of this magnetic quantum number. And the quantum behavior is the discretization, and it is resulting not only in the energy but also in the space, in the motion, in the angular momentum part as well. We will stop here and we'll move further from this point onward how the atomic picture has been modified through the creation of this quantum theory by solving the Schrödinger's wave equation and by reaching at these new quantum states, the new addresses of the electron. And we will soon learn how the many electron systems can be studied, and the interactions between electrons and interactions between the atoms can also be handled with the help of the quantum theory. Let us have a break at this point. Thank you so much.